Alright, so this is Chapter 1, Lesson 1 from this book, California Math, your Common Core edition. These videos were designed to help my daughter, who's currently in homeschool and she's going through 6th grade, and she was learning these concepts. And I wanted to explain her how to find, say, the least common multiple and the greatest common factor. And so I created these videos for her, and these videos are not just intended for students, but also for parents who are maybe looking to help out their kids with these sections from this textbook. So we'll start off this section, Chapter 1, Lesson 1, Factors and Multiples. There's two key ideas they want to introduce here, and that's the GCF, which is short for greatest common factor, and the LCM, which is short for least common multiple. So you're given some collection of integers. Here's the examples that I'll be going through. The GCF of 84 and 45, and there'll be 3 more. And now these are all GCF type examples. I think it's really important to learn how to do one of these tasks first and be able to do it really well and have a lot of confidence before learning the next one. So this video will focus just on finding the greatest common factor. Now when you're doing these types of computations, finding the greatest common factor or the least common multiple, at least for the way that I'll show you, it relies on building factor trees for numbers. So here I want to remind you of what a factor tree looks like. I drew a factor tree for 60. You take the number 60 and you break it apart into factors. So here I broke apart 60 into 2 times 30. And anytime you end up with a prime factor, you get to stop that part of the tree. So 2 is a prime, so I stopped here. 30 is not prime, so I had to keep going. I broke apart 30 into 2 times 15, and finally 15 into 3 times 5. 3 and 5 are both prime, so the tree stops here. And depending on the way you broke apart your 60 in the first step, you might have a factor tree that looks a little bit different. So here I did 60 as 10 times 6, and then I broke apart my 10 and my 6. So even though these trees look different, what matters is that you get the same list of prime numbers in the end. So I have 1, 2, a second 2, 1, 3, and 1, 5. That's the same list that occurs over here, and what that's telling you is the prime factorization of 60. 60 is 2 times 3 times 5. So these are factor trees. And we'll be building factor trees for each one of these numbers here, 84, 45, 84, 280, and so on. Now that's for GCF. We'll do the same thing for LCM, so we'll also be relying on factor trees to solve LCM type problems. So let's go ahead and get started. So we'll start with the GCF of 84 and 45. Our first step will be to build the corresponding factor trees. Now the best way to learn mathematics is by doing mathematics. So if at any time you want to pause the video and try to, say, compute a factor tree on your own, or try and finish off an example, you should. It's okay to get things wrong. What's important is you actually go in and try problems on your own, and if you want to learn them. So 84 and 45 will be our first example. To be real clear here, I'm talking about GCS. So let me go ahead and erase this LCM. We'll come back to that in another video. All right, so find the greatest common factor of 84 and 45. So just, we're going to do some computations, but just to explain what you're looking for the largest positive number that divides evenly into 45 and evenly into 84. I'm going to show you how to find that number. You don't have to do the factor trees as fast as I do. It's not a race. What matters is you end up eventually getting the right factor tree. 84 is 2 times 42. 42 is 6 times 7. And 6 is 2 times 3. If that took you twice as long or 3 times as long, that's fine. Right, and then 45. I can break that one apart into, say, 5 times 9. And 9 is 3 times 3. So 45 is 3 times 3 times 5. 84 is 2 times 2 times 3 times 7. You're looking for the greatest common factor, so what you want to find is the overlap. So what do I mean by overlap? I'm going to look at these two trees at the same time, and anytime I see a common prime factor, I'm going to go ahead and circle that. So I don't see any 2's on this side. I don't see any 2's on this side. I see a 3. I see exactly 1 3 on this side, and that'll match up to this 3. And then I don't see any 7 over here. The greatest common factor in this case is our number 3. So the GCF of 84 and 45 is 3. 3 is the largest number that divides evenly into 45 and 84. So now let's take a look at a second example. We'll do 84 and 280. Since I'm using 84 again, I'll go ahead and keep this same factor tree. If you want to pause the video and try and find the factor tree of 280, then go ahead. We shouldn't be discouraged by the fact that 280 is a decent sized number. It may take us longer to build our factor tree, but eventually we'll get there. So 280, I'll do 10 times 28. 10 is 2 times 5. 28 is 4 times 7. Maybe your factor tree looks a little different, that's all right. 4 is 2 times 2. So our number 280 is the product of 2, it's 2 times 5 times 2 times 2 times 7. Now we look for the overlap again between these two factor trees. I have a factor of 2 in both, so I'll go ahead and circle it. This is just a bookkeeping device. This isn't some kind of process that you have to do to find the answer. I just like these little circles because visually it helps me see where the overlap is. So they both have a factor of 2. They both have another factor of 2, so it's a second factor of 2. See what's left to inspect. And notice I'm only looking at the primes. I'm not looking at 6. I'm looking at the primes here. So here if I look at 3, I don't see a 3. If I look at 7, I do see a 7. And I think that's all the overlap that I could find, because again, we don't have a 3 as a prime factor inside 280. So this is different than the previous example where I just had one overlap. Here I have 3 prime factors that are common to both. So what do you do in this case? Well, for each one of those common prime factors, you build the GCF by multiplying those numbers together. So we'll have 2, our GCF in this case is 2, times, we've counted for that too. We're going to put a check mark there just to make sure we're being real careful with our bookkeeping. I have another 2 right here, so 2 times 2, and finally I have another, or a 7 as a common prime factor. So I multiply these together. 2 times 2 is 4, times 7 is 28, and my GCF of 84 and 280 is 28. So because of the multiple prime factors in common to both, this second example behaved a little bit differently than the first example. Still, the overall idea is the same. Build factor trees, look for overlap, and if you have multiple prime factors overlapping, you multiply those prime factors together to obtain your GCF. Now let's take a look at a third example. We'll do 10 and 39. While I'm erasing, you may want to start building the factor tree for 10 and build the factor tree for 39. Just see how far you get. And 10 is not too bad, but 39 may take a little bit of thought. A hint is 39 is divisible by 3. So third example, GCF of 10 and 39. 10 is 2 times 5, and 39, it's okay if it took you a little bit of time to see this, is 3 times 13. I have my factor trees for both. 2, 5, 3, and 13 are all prime numbers. I look for my overlap. In this case, there's no overlap, so what's the answer? It's not like 10 and 39 do not have a GCF. We don't put the question mark or unknown. What the GCF is in this case, when there's no overlap, it's the number 1. 1 is the largest number that divides evenly into 10 and evenly into 39. And it's because these two numbers don't have any prime factors in common. So that's what happens if there's no, that's what happens if there's no overlap. And you get 1 for your GCF. Now the fourth example, it's a little bit different than the first 3 because I'm computing the GCF of not just one or a pair of numbers, but 3 different numbers. And we could do that. We don't have to change the procedure very much. We do have to be maybe a little bit more careful in the bookkeeping, but the overall idea is the same. So GCF of 30, 78, and 45. So for practice, if you struggle building factor trees, pause the video and give it a shot. If you're pretty confident with factor trees, then that's not them. Just getting the factor tree is a needed step, so we want to make sure we can do that. 70 is 2 times 39. That one's a little bit tricky. 39 is 3 times 13. 45 is 9 times 5. And 9 is 3 times 3. Once again, not a race. It's okay if it took you twice, 3 times as long as you get the right factor trees. Okay, so what do we do when there's 3 numbers? You still look for overlap, but whatever overlap you find has to be common to all 3. So it's no longer good enough if, say, this pair of numbers has a common prime factor, but this one does not have that same prime factor. We need prime factors common to all 3. So if we look at it, we'll just inspect one by one. And the moment I see that, so let me look at this one. 5 is a prime. It's a prime factor of 30. It's not a prime factor of 78. So I get to go, I don't have to pay attention to 5 anymore. Even though it does appear over here, it has to be common to all 3. So I can move on. 2 is a prime factor of 78, but not a prime factor of 45. So I get to move on. 3, I see a 3 here and a 3 here. So that's what I get to circle. 3 is common to all 3 of these numbers here. And that's it. I've checked 5, 2, and 3, so I've kind of looked at everything I can get from this number, and so I just have 3 as my GCF. 3. Now certainly, taking away one of these numbers and kind of changing the problem and just looking at the GCF, say, of 30 and 78, I believe your answer would change in this case. So if you're looking for a bonus problem just to try out, I'll say it out loud, I'm not going to write it down. But what is the GCF of, say, just 30 and 78? Let's pretend we weren't looking at this 45. The GCF of 30 and 78, we saw already they overlap in 3, but they'll also overlap in 2. So it turns out the GCF of 30 and 78 would be 6 from the 2 times 3. But once you look at the GCF of these 3 numbers, then because you need something in common to all 3, you no longer get to take that 2 because it's not a prime factor of 45.